So happy Saturday, everybody. And we're here for exam 2 practice. Here is the stuff that we talked about in the last class, problem types. As I mentioned, I would put more of my emphasis, if I were you, to studying into the 5, 6, and 7 compared to homeworks in 4. Taking a look at the graphic way of thinking about it, I would try at a minimum in my preparation to do a problem that was similar to all of these ones right here, one at a time. Don't have to work them all out all the ways for some of them if you feel comfortable with them, but if you start a problem and you're not able to finish it, or you get something terribly wrong in it, then I would do another problem like it until you felt comfortable. And in making your equation sheets, you might want to think in these terms. Do not write out solved problems on your equation sheets. I'll be collecting them, and I will take points off if your equation sheets have step-by-step solutions, and even worse, that you have solved problems. I didn't last exam, but there's a good chance I may ask you to see your book when you come up to, So anyway, I don't like being a policeman, but I want you to be able to think your way through a problem. There's already example problems in the book, and those should be sufficient if you did want to try to mimic a problem. So anyway, don't like being a negative guy. Let's open up the forum here for questions. Anybody have a request? Once again, you can speak up or do it in chat, whatever you want. Raise your hand if you want to, if it makes you feel better. I have a list. I can see a list of people here, so I can call on you if you want to raise your hand. And, okay, good. We have our first request. Can we do a turbine problem? All right. Well, let's take a look and see if we can find one. Thank you, Andrew. I got to find my mouse first. Okay. In a dual monitor, it's kind of weird because I'm seeing this. I'm seeing this, what you're seeing on my left screen and on the right screen. You don't care, but that's fine. So let's see. Where would that be in the book? Well, we could go ahead. Here's the 8th edition, and I think that would be somewhere in chapter 4. So I'm gonna go backwards, go to chapter 5, and come back up. And let's see. Somewhere up in here. Okay, so this is a turbine problem with a little bit of mix to it. Let's see if they go pumps and pipe channels in this section. And in this section, we have compressors. This section, we have throttle. Here we go. So here would be the section where those problems would be. And let's see, what do we have in our practice problems? That would be, let's see, this is problem 440. And these are all from the 8th edition, so they should match up. So, yeah, so we're actually, this is a problem in the, so let's just do this first one. And then if we want to, we can do a more complicated one. A lot of times, the first couple problems within a section is, they're a little easier. So let's see. I'm going to write some of this down. Oh, now I need to move it over to the other side if I want to be able to see it. So I guess I will narrate this, do my best while we, I know it's just sort of boring. So you can write some of these things down. So we have a steam turbine that has an inlet of 3 kilograms per second. And the inlet is P1 of 1200 kilopascals and a T1 of 350 degrees Celsius. And they gave us a velocity. So that's sort of a clue that we might need to use that more extensive steady state open system first law equation. 15 meters per second. And the exit, so we'll call it P2, 100 kilopascals, so that's atmospheric pressure. And the T2 is 150 degrees Celsius. And V2 is very slow. So that means we're going to ignore the outlet velocity. So we want to find the specific work. That's interesting. And the power. Okay, that's good. Okay, so we want to find out, lowercase w, and then uppercase W dot. I see. I want to see if there was something else into this one. I guess this is this looked like it was a continuation. I guess 42 is a continuation of there. So we could actually look at 41 after this if you want, unless you want to do some kind of extend. So we want to try to unless you want to do some other kind of problem, is what I trailed off saying. So here's our initial conditions. So we should probably look these up in the steam tables in the back of the book. I'll try to get this to, sometimes it needs to see something to be able to focus. And I need to be able to focus. So let's go. Here we go. We'll go to, this is the 8th edition, and the inlet conditions should be superheated. We could check if we wanted to, but I'm pretty sure. So where are we superheated? Where we start the superheated. Okay, there's the pressure entry. Okay, so here we go. And we want 1200 kPa, which is right here. Let's make this wider. And we were at 350 degrees. So right here are our values. And so the most important one that we want to get out of this is H1. It's going to be 3,153. We don't have to go more sig figs than that. I'm going to end it with a 6. So that's kilojoules per kilogram. They're only asking us about first law stuff, but there might have been some motivation if they wanted like a diameter, or like if you know the velocity, then you'd be able to use, and we know the mass flow. So what we'd be able to do, so let's just write that down as a what if type of thing. We're not being asked this, but it's a variation on the problem, and we want to be able to be prepared to be able to answer things that maybe aren't like, that we haven't been asked before. You have to be prepared to answer things you haven't been asked before. That's the level of expectation in this course and every course that you'll be facing. Okay, so now we want to get the probably check this out sometime. Yeah, this might still be superheated. I think it is. No, actually, we could actually decide it has to be superheated, right? Because this is about atmospheric pressure. So then the saturated temperature would be right around 100 degrees Celsius. This is 150. So that's our conclusion. This too must be a superheated. So we come up to here, and yeah, good. This is good news for us. We're able to find H2 at 2,776.38. Make it 0.4. Kilojoules per kilogram. And we don't know anything about the velocity at the exit, and we'll just go ahead and continue with that right there. Okay, so what we want to do is write down what our first, we might make us feel comfortable. It would for me, at least. I'm a visual learner, so it really helps me to kind of picture these things as I'm coming through here. So we have our work out right there. So this is, I can make an association as a visual learner that this corresponds to heat, and I'll write this as in, minus, okay, well, let me first start out with, because of the way they asked this, they asked for this first. Let's use this version of it, right? There's no dot right there. It's on a per mass basis, and minus work out, still lowercase, and that's going to be plus the summation of the H ins minus summation of the H exiting. I'm just trying to be consistent with what they're asking right there. Right? This is the same. I don't know if I don't like the summations here actually, because this really would work out. We're doing on a per mass basis, and so we can't separate things out. So this will only really work for one in and one out, because the mass flows matter for the thing. So this would be the only version that you would use for this right here. I guess the alternative to this would be, I actually kind of prefer this one right here. Right, so and that's supposed to be lowercase, and this is supposed to be uppercase. It doesn't quite look like they're different. And then this is the one where you go in, and M dot exit and H exit. All right, so they did tell us what this is right here. So I'm going to go ahead and go with this. I've changed my mind. We'll just say in a little thought cloud that we could have done it this way. We'll do it this way and then later find that. We'll find this first. So we're going to assume this thing is well insulated, right? That means there's no Q dot is not coming in or out of this thing. So it's just simply going to be here. And so working here, and we're just going to bring this onto the other side. The M dot, so we go M dot is going to be H, and the inlet is 1, and the outlet is 2. So we have 3 kilograms per second, and we have 3,153.6 minus 2,776.4. And
question.
Okay, yes, sir. 1 second. Here,
Okay.
No problem. No problem. I just want to finish this and then let people like write the thing down, and then I can start talking. So if people are writing things. 776.4 minus 3 times. So we're going to get 1,132, and these are going to be kilowatts. And then if you want to get the work out on a per mass basis, all you have to do is divide by M dot, or 1,132 divided by 3 kilograms per second. And then we would get 377.2. And this is going to be kilojoules per kilogram. Okay, go.
I was going to ask if we're always able to just assume that the thing is going to be insulated to cancel out the Q. If it doesn't say otherwise, do we just assume it's insulated?
Exactly right. Yes.
Okay, perfect.
There were some problems where they said, what if it lost this amount of energy? If in Dr. Yevstrick's, I think one of his questions here, let's see, he said, provide assessment of thermodynamics here. How would the thermodynamic state change if the nozzle were not adiabatic and could lose this energy? So that's kind of like the same. This one happens to be a nozzle onto the thing, but it's sort of the same problem where sometimes you might, because in real life it can lose some heat. There are some heat losses coming through. Like right here. So like he had this problem right here. Yeah, I thought that he did have one where he had this 5 kilowatts of loss. Let's see. Kenzie asks the question. Oh, she's asking me. Okay. How do I do that? Okay, I got to do that. Okay. Why do we choose the more extensive equation? And can you remind me what the difference is between the lowercase and the uppercase? Excellent question. So the uppercase, the lowercase is on a per mass basis. So we do a lot of things that way because it kind of sets us up for later things that we do. We try, and we've already kind of done it a little bit, is to try to have a generalized steam plant, right? So that we'll figure, or other types of equipment where we won't know the mass flow yet. So we could just do everything on a per mass basis. That's the lowercase letters, and still be able to find something like the efficiency, right? We're able, even without knowing what the mass flow is, we're able to find the efficiency, and then you could just ramp it up for whatever size of a power plant, whether it's a gas turbine, or even do this with gasoline engines and diesel engines and other types of cycles. That's the per mass basis, is sort of a more generalized thing. But in here, we're going to have the uppercase one, and that's going to be because we multiplied it by the mass flow. So I should have maybe written this thing out, that this is equal to this right here. And the same thing here, if we had in or out, this would have been mass flow times lowercase q in. So this has some advantages for us, because we can just make it more of a generalized thermodynamics of a system without knowing what the magnitude is of the actual flow that's coming through there. I hope that helped. And in terms of like the longer equation, I also, I just messed up. So here we go. I just made a mistake. And thank you for asking me, because let's see what the difference is. Okay, so this was an oops. Dr. Deal made an oops because his brain doesn't work very well. I should have actually up here used the alternate equation. Here's the alt, because velocity was involved. So I could say equals Q in minus work dot out plus the summation of m dot, and I'm going to try to fit this all in. We can go h, this is supposed to be I right there, I plus vi squared over 2, and I'll include this, but it's not going to matter. We're going to cross it out. Gzi minus summation of m dot exiting he plus ve squared over 2, squeeze it in, gze. Okay, that's the one I should have used, and my brain just wasn't working. So there is no height change right here, right? We don't know anything about it, so we're going to assume that didn't. They said this was very, very small, and since it's it's very small, and we squared it, it becomes very, very small, so we can ignore it. So we did have this, so we should include it. And like I said before, we don't have heat coming in or out, so we could bring this work back onto the other side, or the power out. And so we're gonna, the m dot's the same in and out, so we could bring this thing out over here. And so we're going to have H1 plus V1, because that's the entering, or inlet, I guess would be the better one. Entering, unfortunately, starts with an E as well. And this is the exiting one. And that's going to be minus H2. So we have to be careful with units here. We have to remember that this is going to be meters per second, and we're going to square it. So it's going to be meters squared per second squared. And what that really is going to be it's going to end up being a Newton meter per second. So instead of these are kilojoules, which are kilonewton meters per second. These are kilojoules per kilogram, I should say. I said per second. I should say per kilogram. This right here. This was we need to divide this by 1,000, because it's going to be too large. But anyway, let's check it out and see what happens. With the values, right? So we had that same value as up above, 3,153.6, but now we're going to go plus, and this is, we were told it was 15 squared over 2, but we also have to divide by 1,000. And we can go through the units there in a second for this to demonstrate this. And then minus our 2776.4. And let's see what that value is going to be. So that's the, really we're just going to do 15 squared divided by 2. And that's still only 112.5, but we have to divide that by 1,000. And then add it, boom. So we get 1,132 again. We note that it just had it was a round off error right here, the velocity. And if you wanted to double check that meter per second, and this was squared. Well, notably, let's see how I'm gonna do this. I'm gonna try to think about. Let me go the other way around. Let me go that if we had a joule or a joule per kilogram. This is kilojoules per kilogram. So what if we had a Newton meter per kilogram? Well, a Newton is a kilogram meter per second squared, and that's per kilogram. And this also was a meter right here, right? So what I have right there is a Newton turns into that. And then your kilograms cancel, and there's 2 meters. So this is the same thing as a meters squared per second squared. And notably, I just did a Newton meter, right? So this thing turns into a joule per kilogram, but we have kilojoules per kilogram. So that's why we had to divide by 1,000. I hope I didn't make that too confusing. And sorry about my oops right in here. I totally forgot, but you could see that it didn't matter in my answer. That the kinetic energy was really kind of unimportant compared to the enthalpy. So that's why a lot of times it will be ignored. Is there any other questions on that? Do you want to go to the?
I have a question.
Okay, great.
So for this problem, we got to both the right answers without using a velocity. Could we just have not used it in general?
I think so. Well, on the exam, I'd like you to try. All right, I'd like you to recognize that you needed. Unlike me, now, we learn from my mistakes. So learn from my mistake and actually investigate this because you don't know for sure if you can ignore it.
Okay.
You can. It turns out you can, but it'd be good to just demonstrate that we know that this is something that we would often have to come up to.
Okay.
So if you were to take a look. And I encourage you to use the book in conjunction with your exam preparation. And when you're writing out your equation sheet, I wouldn't write every single thing. I think it'd be a waste of time to write every single equation because that's actually kind of worse for you. I think sometimes is having too many equations. Open book does present itself with challenges sometimes because you're almost got too much stuff to look at. But here you go. Here's your instantaneous process, and notably that they've put this right here. But we know that this is going to be 0 for the steady state. But here is where they call this an H total I, and here's where your H total I is right here. So here's why I wrote down that version of it right here. They decided not to include that right here, and they've also decided to rewrite the thing out so that they have these like this on the left-hand side and this on the right-hand side. I think it's better to write it the way that I have it right here. This is more of a generalized equation, and even here is even like a little bit more generalized right here. It's a good concept to have down. But either way, it would get you to the same place.
Okay, thank you.
You're welcome. So we got requests for the next problem, or I could keep going, whatever you want. Like so, this I think a lot of the turbulent problems are very similar. It's just sometimes they'll throw like there could be like a little wrinkle in here. So here is like one where we have they've put a little bit other things in here. You have an expander, a turbine, and with heat transfer, right? It's helium that makes it more complicated. So I don't think we have helium properties. Don't think so. I'll double check. So we might you have to use the ideal gas law and use constant specific heats for this. And so we're showing this thing, and then it also they have the outlet, the power outlet. So we want to find the heat transfer as part of this, and they're also saying this right here. So it's kind of a twist a little bit of a twist, not too much of a twist, but it can take you out of your comfort zone. So maybe it's worth peeking at this one. Unless you want to do another problem. I'm totally down with doing another problem. Going once, going twice. All right, we're going to do this problem. So this is 449. And then after that, we should probably do some stuff that's in closed systems because there could be quite a few little wrinkles and things put down here. So let me write down this stuff. We have 0.05 kilograms per second, and this is helium. And P1 is 1,000 kilopascals, and T1 is 550. And they went ahead and made Kelvin. I would have given it to you, and maybe that's a jerk move. I would have given it to you in degrees Celsius so that you had to change the thing out because it's. I tell you what, people make the mistake all the time with ideal gas law, and I want you to remember to use it. I don't know if that's a jerk move or not. So the power out was 55 kilowatts. So what we're going to need to do is find Q dot out. So the heat transfer rate neglecting there. All right. So, but by the way, actually heat could be in. You don't know. So let's just say, well, I won't even. I'm gonna. So the sign conventions can help us if we don't know whether the heat's going to be in and out. So this is this is still a turbine, right? So we have a question of whether Q dot is in or out, but we do know what the shaft power output is going to be. So this is 1 and this is 2. So let's look up and let's double check about helium's properties. What has been provided? Because it's possible that there is such a thing as a helium table. I don't know. I've never seen one. I don't mess with helium a lot. So let's see. It would be here in these properties. Oh no, that's not true. It might be up here. Well, first let's just assume that there isn't one for the time being, and we'll go to the ideal gas properties here and get the R and probably the CP because that's the one that we associate with enthalpy. And so here's our helium right here. So R for helium is 2.0771. These are kilojoules per kilogram degree Kelvin. And our CP is going to be equal to 5.193, and also kilojoules per kilogram degree Kelvin. But let's take a quick little perusal through this section because there are some tables like this one right here for air. And then we also have some here. We have nitrogen, we have oxygen, carbon dioxide, water. I don't think I would use these for water. I don't know why we have them for water, but we could actually double check these because this is should be kind of redundant. But we don't need to do that right now. We got diatonic nitrogen, we got monotonic nitrogen, we got diatonic oxygen. I thought we just did that. Didn't we just do oxygen over here? We had diatonic oxygen here. And what's the difference over this one? Oh, okay. We had these things right here. So I don't think we have helium. That's my conclusion. There's no helium tables to be doing it. So we must have to do this via ideal gas law. So don't think there's any need here. Dub, I'm thinking. I think we could just do this with this right here. Yeah. So our first law right here is going to be equal to Q dot, and this is going to be in, assumed in. Here's going to be out, and then plus summation. And then I don't know anything about velocities, so I could totally just go for this equation. Same one we just did a minute ago. And these are both E's. We're trying to find this. So we're going to go equals, here's our Q dot in, minus, they told us it was 55. And when we multiply this m dot times this h, we are going to get kilowatts, so we're okay with that. And so we're going to go m dot, so we can go m dot cp T1 minus T2, right? So because we could say that delta H is equal to, well, no M's, Cp delta T when it comes to ideal gases. Or other things, like we can't actually do this with water. Actually, we could compare to what we get from from looking at the enthalpies. So a simplification for water is to use the specific heat. It's an option. So let's put, I jumped the gun in putting a value in there. So minus 55 plus the flow is 0.5 was given. CP was 5.193, and we were given these in Kelvin. So it went from 550 to 300. And I should have in the other problem maybe checked to see if we got the right answer. I'm going to keep track of my signs really carefully. So let's see. We're going to have 550 and 300. Subtract that, multiply by 5 point. What? I just screwed up somewhere. No, that was right. Okay. 5.193. Boom. 0.05. Boom. All right. So that comes out to 64.91. 64.91. And we're going to subtract 55 from that and then bring it over to the other side. And sure enough, it's going to be negative 9.913. And these are kilowatts. And that negative indicates, well, it's not in, it's actually out. So Q dot out is 9.91 kilowatts is what we would say for the thing. And if we were to check it against what this was right here, we say 9.9. Okay, cool. They decided to go with 2 sig figs, but what do I know? Let's go back to this. So just a slight variation, and one of the important things is trying to keep track of the signs, because this takes care of that. Silence. Anybody got a question or a request? Let's see. Let's jump over to. I can't find my mouse again. There you go. Let's go jump over to something in 3. We got one of these little guys right here. Oh, we got. Can we do a pump problem? Sure. Let's see. I got to try to find where the pump problems are. I'm trying. I don't. My recollection isn't all that great. Do we have pumps in here? No, this pump should be in chapter 4. I'm going the wrong direction. So let's see, transient processes, pumps and channel flow. An irrigation pump takes water from a river at 10 degrees Celsius in an open channel. So I'm not sure if we did any open channel things, where it flows out at 10 meters higher. Okay, I don't think, no, I think we're okay, yeah. And the pipe diameter in and out of the pump is 0.1 meters. And The motor driving it is 5 horsepower. What is the flow rate neglecting kinetic energy and losses? All right, so this is an interesting one. I don't think we need that. We don't need anything to do with temperature. All right, so I don't know. We might have a better problem coming up here. Water flows from one building to another in the winter. The pipe loss has to be to 5 watts of heat transfer. What is the minimum required mass flow rate that will ensure? Let me jump over to here. So this is a 475 range. Uh, 479. There you go. Let's go to 479. So 479. And consider a water pump that receives 25 degrees Celsius. P1 is 100 kilopascals and delivers to the same diameter. So in and out equal the same thing. Short pipe with a nozzle and exit diameter. So D is 2 centimeters or 0.02 meters. 2 atmosphere. Neglect the kinetic energy in the pipes and assume constant U for the water. Find the exit velocity and mass flow rate if the pump draws 1 kilowatt of power. Okay, let me think about that. All right, so we have, I'll bring this over to the side so I can keep looking at it. No, I can't bring it over here. I actually have them printed out, so let me put it back over here. Where'd you go? Boom. All right. So where'd you go, guy? And this is problem 479, and you 479. And what is the answer? 479. All right, so we're aiming for somewhere in the range of 18.55 meters per second. Okay. All right, so one of the pump things that we will look at, and I don't think we have a temperature difference, right? It says it comes in at 25 degrees Celsius in this, and it delivers it in the same diameter short pipe, having a nozzle exit area diameter and having a nozzle with exit diameter of this. So this is the nozzle exit diameter right here. So let me see what does that look like. We're going to pump right here. We've got inlet right here. Here's the pump inlet. Here's the pump outlet. It's short, but I think it says it's having a nozzle right here. So I think that's what they're implying, is that there's a nozzle right here. So we want to find the exit velocity. So I'm going to call this 2 right here. So we want to find V2 and the mass and m dot. Okay, and we are putting in power right here. So we have this flow rate coming in here. So this is 1. I'll be honest, I don't quite know whether, I guess I'll just think my way through it. That's the best way, just to demonstrate, think your way through it. So we're going to go Q dot in minus work out. But in this case, by the way, that's good. This is going to be work into the system. Then go plus, and we'll go the summation, and this is we'll use the bigger one, I guess, as part of this. Is that going to be true? Let me think about it. Let me think. I didn't memorize these. And I didn't want to, I already messed up one, so I didn't want to mess up another one. So I'm gonna cheat and take a peek. Where'd you go? Yeah, I want to say, so this is in, I guess I'll do this right here. I'm pretty sure this is what they're getting at right here. GZ in minus summation M dot exit, and then all the same thing. We could do this. I think they say they don't care about the velocity, so I would almost make go in between here and here, and then go from here to here. Except that we don't know what this is right here. I guess this is, maybe these are going to be slow enough, and this is going to be what we have coming out of the thing. Gotcha. Okay. All right, so we know that's gone. And oh, I know what I could do. Okay, so I had my aha. Maybe. That's gone. That's gone. I think we're going to go ahead and say, oh, I know. All right, I see. We're going to say that P1 is equal to P2. I think I'm going to make that 2, and I'll make that 3. Sure. So this is one of the ones where we were also for a pump. Gotcha. That HI is going to be equal to HE. I don't like what they did here, but okay, we'll set it equal to HE, which is equal to UE plus P E VE. Gotcha. This right here has all been, I've written all this down. I shouldn't have, but I did take a peek at the solution manual. We can see that like if the P's are going to be equal to each other and the U's are going to be equal to each other, we could go ahead and decide that the T's are going to be equal to each other, the temperature in and the temperature out to the thing. And so what we could go ahead and cancel those out because that's going to be equal to that. What I'm left with is yeah, so we're going to have negative work out. It's going to be plus M dot. Excuse me. Wait, 1 second. Okay, yeah. This guy right here, he's going to be 0 because they said that these were going to be equal to each other. So it's going to be very small. That's going to be very small. So I'm changing my mind of that, going back to that. So this is going to be the minus because it's going to be this guy right here. This is all that's going to be left. M dot, and this is the same M dot, so we're going to make it there. This is going to be V2 squared over 2. And remember that this is going to be probably divided by 1,000. Oh, okay. All right. So this is sort of a bastard. This is a bastard of a problem. What is it? What stumped me the full time is that I wasn't sure how we were going to get rid of mass flow because we were told, and this is a mass flow right here. So the trick as part of this, I hate these stupid tricks, but this is a trick. We want to use the conservation of mass. So this is a problem that's like it would take me like a little while, on my own looking through the thing before I had my aha moment. That we would have that the mass flow is going to be equal to the 1 second, please. Can be equal to the volumetric flow times my specific mass, right? No, divided by my specific volume, and that we could then that's can also be the area times the velocity divided by the specific volume, and we know this, and we could look this up for that temperature. But we could also just go and say we're going to assume, just for time's sake, that that is true, and it usually is for water, right? So we have this for water, and we can find area, so we could get what the mass flow is. So we could actually calculate this. Could have calculated this thing. No, we don't need to yet. We don't need to. We could go right to here. So there's the trick. And by the way, this is going to be negative right in here because it's in. Is that true? Yes. All right, let me see what your chat is saying. ONG? Since this one is so tough, might as well leave it off the exam. Yes, true. But I mean, this is just a variation that I'm mentioning to you that, and an explanation is due. You're owed an explanation of how you would go about solving it, right? So I'm just looking at the signs right now that we need to put into this right here. This is going to go over to the other side, and so the negatives are going to cancel out. So this right here is going to be equal to m dot v2 squared 2, which now we could go ahead and put the m dot into here and go that this is going to be a times v2 over specific volume times this squared, right? Because now it's going to be cubed divided by 2. And so and we have to be careful here with the units because we were told it was 1 kilowatt. So it's going to be, so let's make it 1,000 watts, right? So these are going to be, and so that'll be working out. And our area is going to be pi over 4. And the area is, let's see, the diameter is 0.02 squared. And we don't know the velocity, but it's cubed, right? Because multiply it there. And we're divided by 0.001 and 2. And so our velocity 2 is going to be the cube root after we do the values right there. I mean, it's not an impossible problem, but it's just going to be, it would just, I don't think it would be a fair exam problem. It isn't, I wouldn't call it too hard. I would just say that it wouldn't be a fair measure of your mastery of the material, in my opinion. But I got to tell you, it probably would be asked by some professors. So we're going to take the cube root of that. And I get 18.53 meters per second, which is what we were told. When we were looking up in the problem, where we go? Yeah, 18 right there. So 18, and then we go back to the other part of the thing, and so the mass flow rate, m dot, is going to be equal to, we'll just go to that right there and go, well, might have been faster to have written that out. So we have 18.53 and divide it by 0.001. So 0.02 squared times pi squared 4 divided 0.001. Boom. You get 5.823 kilograms per second. Not a terrible problem, but not one that I want to do. So no pump problems on the exam. I would not say necessarily no pump problems on the exam, but we haven't done a lot of them. Actually, I don't know if we did any homework problems with any pump problems, did we? I generally don't do that. Yeah, we didn't really do any pump problems. You don't see any in here. And in terms of that section, I don't know. I think I did an example with one, and I pointed out that like we didn't really even find what sections is out of actually. Pump nozzles. Let's see, pumps. And also another thing about pumps is we do a lot of that in fluid mechanics, and we use some sort of a different. It's a whole section. Like there's a lot of the pump things, and we don't really pay attention to the temperature changes in them. But this is like in the book. Here is a pump problem right there, and they say compressors and pumps. It's funny though, they don't really put in like right here is where they this is really where they so that one equation that I wasn't ready for right here. It's this equation right here where they and they don't even talk about it in the book. So I don't know. Yeah, probably no pump problems. I think you could say that. So let's look at another problem. So we need to get a request. You can do any of these if you want to. Like I said, I posted the solutions to them. And then I do think some stuff in chapter 3 is worth going over. I was going to suggest, I don't know, it just jumped out at me. This guy right here, as I think people struggled with this type of problem. So unless somebody wants a different kind, you can name it. Is it okay?
No, we could do this one.
All right. Cool. Let's see. I'll write this shit down. This is problem 3.111. 3.111. And we got this little figure to help us envision what we're talking about.
What kind of problem type would you call this one?
Giving it a name. Well, it's similar to. See, did I close that thing down? I guess I did. Similar to this guy right here, right? So this is a constant pressure, then a constant volume is what I decided to call it here. But it's like because you got one with a stopper in it, right? So it's like you almost had to do this kind of in stages because it's going to have a certain type of process right here, and then something else typically happens after that. So I'll write down that it's let's see, problem 310. So I can read it off of the page while you're watching me read it off of the page instead of doing it the other way around. It's not a very good picture. But they do say, let's see, the piston has the M, 0.1 kilograms of water, and the temperature is initially at 500 degrees Celsius, and the pressure is 1,000 kilopascals. And they say that this thing stops at about 50% of the way down. So not drawn to scale, but you could say that V2 is equal to 50% of V1. Right. So these stoppers come in there. The water cools to room temperature. So T, I guess I almost want to call it 3, but it's because there's two things that are happening, but I'll call it T2. So something might happen somewhere in here. So it's going down to 25 degrees Celsius, and so heat is leaving this thing. And the thing that we want to try to find, right? So first they say sketch the PV diagram, and then we want to find P, and they're saying final. So I would say I guess I'll write F and VF. So we don't know, we don't even know for sure that this thing has gone all the way down and hitting the stops. But why would they tell us about the stops unless they did? But it could, but during the cooling process, it could hit these stops and then keep cooling to 25 degrees Celsius. So you have to kind of like have like that, this narration of what happens in here. And we want to find the heat transfer and when it's not a dot, sorry, because there's no mass flow and there's no time, there's not per time thing happening. So so we have these right here, and it's not going to be little small q and little q because we know the mass. All right, so our first thing that we want to do as part of this is get what these properties are going to be. So we're going to look up into the tables and find in B, okay, so I honestly I just had my aha moment here for me on how to do the problem. First one, we're going through the tables, we'll find in the 1000 kPa right here, and we were at 500 degrees, so here we are right there. And we might want to remember just in these topics right here, I don't think enthalpy had been introduced, and most of the time when we're dealing with these closed systems, we're dealing with internal energy. So the ones that we actually want to write down for this are going to be V1 is now going to be 0.35411 cubic meters per kilogram, and U1 is going to be 3,124.34 kilojoules per kilogram. And what my aha moment was is that from this information, we're going to be able to figure out what the full volume is going to be because we have the mass. So we know this initial right here. So this is sort of like one of the first keys of the problem is putting our detective hats on, recognizing we can find what V1 is going to be, and now we know what V2 is going to be. And then because of that, we're now going to have lowercase v2, right? So so we can get V1 is, I gotta be careful with these sometimes. I get myself confused. If you wanted to find, I'm going to write this over here. If you wanted to find this, you would take this and divide it by mass, right? So here, if we know what that is going to be, we just multiply it, right? So it's just going to be m times V1. So 0.1 times 0.35411. So we know that this is going to be 0.035411 cubic meters. And therefore, V2 is going to be 0.5 times that. So I'm going to go ahead and put that into my calculator because I'm not going to trust myself with that. 0.5 times it. So it's going to be 1/2 that. So it's 0.0177. I'll cut it off at 4 sig figs. And therefore, V2 is going to be V2 divided by M, or 0.01771 divided by 0.1 kilograms. and shouldn't need to do that in my calculator, but I just did anyway. 1771. And so these are the cubic meters per kilogram. And I probably could have just multiplied this by 0.5.
Where'd you get the 0.5 from?
The 0.5 is the mass. So this
Was
should
that
have
given?
been, yeah.
Okay. Yeah, I thought the mass was 0.1, not 0.5.
Oh yeah, what did I do? Oh, I'm sorry. That where did that 0.5 come from? Sorry. That was 50%.
Okay, thank you.
Yeah, you're right. Sorry. I should have written this equation out right here. This is the same equation as that right there.
Okay, thank you.
Well, please ask if you're okay. So what we know now is that at T2, let me see. All right, so there's going to be a trick right here. No, okay, so as soon as okay, so we're going to get, we have this specific, let's find out.
I have a question about us finding the masses too. Oh, never mind.
So we're going to have P, V, and we can go either big P or little v. And we're going to have these guys right here. And it's superheated. So we're going to go and we're going to reduce. Is this true? Is this? Oh, yeah, this has to be a constant pressure. One thing you should know is that this first process from here down to there is a constant pressure. And you're going to ask yourself, why is that a constant pressure? It's because this thing weighs something. And as you're removing heat, it always weighs the amount that it weighs. And it always has the surface area. So it has to be a constant pressure process. It's one of the key ingredients of any of these problems is to remember that has to be this scenario when there's no forces or springs or anything on this is constant pressure. So we're going to be coming down. Dummy, sorry. We're going to be going sideways right here until we hit something, right? And it's actually going to be 1/2 the volume going sideways. And then we're going to keep on going downwards right to here, right? And we don't quite know what that is. So I'm still a little uncertain because I haven't memorized how to do this. I'm just thinking my way through it on how we're going to get to this state. But let's keep moving on. We're going to get to this specific volume and then come downwards. So we can find out what these properties are going to be. Yeah. So what we'll do, here's what we'll do. We will go to, because I got it now. I got my aha moment. This pressure right here is known. So we can look this up. We have this specific volume and we have this at 2. Right. So I would actually label these states 1, 2, and 3. So we're going to find 2. At 2, we're going to have P2 and V2 and look that up. So P is still 1,000 kilopascals because it didn't have any choice when it got just before it got to right here, which is this point right there. And so we're gonna probably check the saturation one. That's a good one to do, right? So we're gonna look at table B.1.2. Because it's indexed with pressure, and we're going to look at 1,000 kilopascals, so right there, and then we will look at specific volume, and we can see that our specific volume is in between right here and right there. So it must be saturated those conditions. So I'm going to write these down, and I'm also did I just yell? What happened there? VF is 0.0 0.01127 cubic meters per kilogram, and VFG, I'll need that in a second because I want to need to get the quality at that halfway point. And then I think I need internal energy. Do I need internal energy right now? I think I do. I think I do. I think I need UF is going to be 761.67 kilojoules per kilogram, and UFG. I hope I won't waste my time, but I think I'm going to need that right here. Okay, so my first thing to do is to find out what my quality is going to be. And so I have this, so I'm going to put it into this equation here. And I have 0.1771 equal to 0.001127 plus my x2 and times 0.19332. And I'll get my x2. So subtract out 0.01127 minus, I go 0.19332 divided, and we'll get that it's going to be 0.9100, so 91%. And I'm pretty sure I need this U, so I'll go ahead and use U is equal to UF plus X times UFG, and find out what the U2 is going to be, 761.67 plus my 0.9100 times 182.97, and I did get my U before. I'm going to get 182.97 times 761.67 plus, and so this is 928.2 kilojoules per kilogram. Notably, before that we started out with 3,124. So the thing that we're looking to get is we're going to say that's going to help us with the amount of heat and work that came out of the thing. And then I think for the next process, what we're going to have to do is go through the other table and find the 25 degrees. So yeah, so at T equals, and we'll call that 25 degrees Celsius. And what we'll find here, 25 degrees Celsius, and we'll do the same thing, which is to say that we don't need to see that. We will get, yeah, you can see the specific volume. We have that same specific volume, which was 0.1771. So going back to why we're doing this is the specific volume can't change once it hits this stopper because the mass doesn't change and the volume doesn't change. So we're going to get the same specific volume that we have right here, but now it's going to be at that 25 degrees. So I should probably have made that 3, because we could say that this is state 1, state 2, and then when they get done taking the rest of the heat out, it's going to be at state 3. So this is also going to be equal to V3, if you will. So this is also V3 is equal to that because it hasn't changed. I hope that makes sense. So we have V3 equal to 0.1771 cubic meters per kilogram. And now, so we go for that table, we will find these values right here. So VF is equal to 0.001003 cubic meters per kilogram. VFG is 43.36. And while I'm here, UF is going to be 104.86 kilojoules per kilogram, and UFG is right here, through 2304.90 kilojoules per kilogram. And what we will find is knowing, once again, I'm going to write down this equation right here. I'm going to get the next it actually I guess it should be the different amount, right? So when you could think of it in this terms right here, that we found, here's the width across here is where we were finding that 90%, but now it has gotten wider. So even though it's gone straight down, where it lies in terms of the percent of the thing is going to change. So it's what we have to find using that specific volume. So we'll write out that the 0.1771 is equal to 0.001003 plus x3, call it, and then it's going to be 43.36. So x3 is probably going to be a pretty small value, or small. It's going to be smaller. So 0.1771. 0.001003 subtracted out, divide by 43.36, and we end up with, that is a very small, 0.0046 406.061. So 0.4%. Pretty damn small. I want to double check that, just because anytime I get something that I don't, that seems like it could be a mistake, I like to check. And I know that slows us down, but it's so easy to make mistakes. No, I get the same value again. Okay, so now what I'm going to do is I'm going to find what U3 is going to be, which is going to be this 104.86 plus that 0.004061. So it's not going to be a lot more times that. And that's times, although this is a large number. Okay, so 2304.90 and 2304.9 times. Okay, so not a lot, like 9.36, and then you add it to 104.86, and you only get 114.22. All right, so this is, I know this is a long problem, so would make for a very long exam problem. Not very long, but it would not be one that you couldn't ask many of these. Let's see. Okay, so our main equation that we were going to use is going to be equal to, for the internal energy ones. So we'll see. Let's take a quick peek at, before we write it down, where we get it from and why it should be on your equation sheet. It should be right here. No, I guess it's to the end of this. Here's the summary. Right, so here should be the equations, and which one will I write down next? Basically, I'm going to be writing this equation down, which, this is basically the one I'm writing down. But I'm going to make these U's instead, or M times. Here you go. This guy right there, kind of like that. Except you see that they've. So we, I think I'm right. I think I'm saying that the right way. U2 minus U1. Yeah. I'm looking at all the other ones. Yes, okay. So U2, that should be a capital U, minus U1. It's going to be equal to Q1 to 2 minus work 1 to 2. And so that's the same thing as saying M U2 minus U1. It's going to be equal to Q1 to 2 minus work 1 to 2. All right, so we know these two things. Yeah, I guess we could combine them and make it to we can really go U3 to 1 if we wanted to, but maybe I'll do this in 2 steps, right? U3 minus U2 equals Q2 to 3 minus work 2 to 3, right? These are different. We do it in 2 steps. What we don't know is the work right here. So we will go ahead and go back to the beginning and take a look at how much work is taking place here. Well, the work, remember, is going to be equal to the that right there. Well, this is a constant pressure process. So it's really just going to be the pressure. So this is going to be the 1 to 2. And it's going to be P during that period times V2 minus V1, right? Because you're integrating across that thing. And so we know what that value is going to be. The pressure on this is kilopascals. It's going to be 1,000, times the velocity, the volume, which we have, right? So we have volume. Okay, so actually what we could do is just multiply it by this V2, because we know this is half of that, so the difference between them. But maybe I'll go ahead and write it out the right way. Yeah, so V2 is going to be 0.01771 minus 0.035411. And you notice it's going to be negative, right? Because this one's bigger than that one. And therefore, work would need to be put into the system, right? Because work is typically out. So that's, these conventions are meant to help us, but sometimes they could be more trouble than they're worth. But we can, what it essentially says that this is actually gravitational, if tell you the truth, energy. But we don't know the mass of the piston, but we do know that the piston has created this. So this is because of the piston falling down and putting energy into this. That's why it's going to be negative, because the negative sign that's inherently in this equation is all about work getting out of the system. I over-explained. But anyway, so we're going to have a negative, and we're really just going to take 0.01771 and multiply by 1,000, basically. So we have negative 17.71. We call it kilojoules. Yeah, we call it kilojoules. Yeah, okay. And then the next part of it, so knowing that we have to go to between 1 and 2, 2 and 3. So 2 and 3 happen at the same spot, but there's no change in volume. The work between 2 and 3 is equal to 0. All right. So what we could do now is to come back up and find out how much heat goes out at Q1 to 2. So that's going to be the mass of this thing, which is 0.1 times U2. And U2 was found to be right here, 928.2. And then U1 was a much larger number, 3,124.34. These are kilojoules, and that's a kilogram. So this is going to be kilojoules. Yep. It's going to be equal to Q1 to 2, and then minus 17.71. So my Q1 to 2, it's going to be 928.2, 3124, subtract it 0.1 times it. All right, so on this side, we're going to get a negative 219.6. And then we're going to move this over, and that's this was positive, but that's going to come back over there and be negative. So it's going to be 17.71 minus. So you have a negative 237.3 kilojoules, right? So that's what's happened between steps 1 and 2. But now we also have to go between steps 3 and 2. So that's going to be the mass is 0.1. This is going to be stage 3, which is only 114.22. And minus 928.2. So you can see we could actually have done this in one thing. I was merely breaking it down because that's how my brain works. 2 to 3, we already established that that was going to be 0 right here because there was no volume change. And so Q2 to 3 should be, once negative, and go 114.2 times minus 928.2 minus then 0.1 times, and so we're left with negative 81.40 kilojoules. And so the total amount of heat between 1 and 3 is, I'll just put those together, and it's going to be a negative 318.7 kilojoules. And I'm hoping I got the right answer. And I did. Oh, they did ask for the one thing I forgot to do. So this, we could say that the Q1 to 3 is going to be 319 kilojoules out. They did ask for the amount of work in the thing, and so that's the work. 1 to 3, I guess, because it's the entirety of the work, is going to be 17.7 kilojoules, and this is going to be in. And the final pressure, P3, we could go back to what we had here, and you recall we went down to it's just going to be the same as the temperature, it's going to be the same as the saturation temperature at 25 degrees. So 25 degrees. Did I get that right? Ooh, wait a minute. Did I get that right? Yes. Okay, it's the right degree. Yeah. So 3.169 kilopascals is the final. So yeah, I know that was a long problem. Not a fun problem, but it's and I'm not going to ask one that's going to be this long. Or if I were to ask one that's going to be this long, which I don't think I will, but it would be, I'm going to ask a challenging problem. It's not going to take this long, but it's still going to be doable. It's not easy to write an exam that's like that, but I will somehow. Does anyone have a question about what we did? Anybody have another requested problem? I see Kyer is up at top. Does he want to ask me anything? Do you want to ask me anything, Kyer? Yes, no? Would you like to see my dog? Layla, come here. Come on up. Come on up. Come on up. Come on. Yeah. Oh, she loves me. See, we gotta see the dog. See the people. Say hello. Hello. Oh, she's a lover. All right. So, anybody want to ask a question about Layla? Why are you this color if you're a golden doodle? That makes no sense. Makes no sense. Make no sense. Okay. Well, ask a question, guys. Come up with something. Anything? Hello. Want to get down? You want to get down, don't you? We're asking questions, right? No? Yes? Let's go back to this. We'll share the screen. Okay, well, I'll ask a question. Let's take a look at one of Dr. Yevistruk's other exam problems. Let's see. Maybe I gotta pick one. Let's see. We had a nozzle. I think we did the nozzle in class. We had a mixing one, right? I think we had a mixing one. And a boiler. What's the hardest problem that he did? So that there was another nozzle problem. There was a mixing problem. I don't know if they were just time consuming mostly. Did we do the refrigeration one? Did we do the refrigeration compressor? Yeah, we did. That was a tough one. I mean, it wasn't that tough, but I think there was a twist to it that made it you kind of had to, you did have to write out the cycle to be able to do it. It was important. Dante's joined this session. He was always here. Must have left and then come back. So let's see. One where you notice we had argon, helium, and nitrogen coming into the thing. We don't need okay. This boiler one was actually a trick one because it was a mass flow problem. It wasn't really all you really needed was the properties, and you had to one tough thing is you had to get the average. Yeah, so that was sort of a trick. You had to get the average specific volume, because otherwise there wasn't like a real easy way, I don't think, to be able to do this. But this was trying to find the areas. Yeah. 3. Let's do this problem. All right, that's cool. We got to do something. We're here. We might as well do something. Or I could just let my indecision take over. Maybe I will. Make my indecision indecisive. Because I did, let's see. Maybe I'll do a heat exchanger problem. Although I was thinking about doing one of these. Let's go for a polytropic process. We haven't done a polytropic process in a while. So I'll try to find one out of our list of polytropic processes. Try to find the word polytropic somewhere in here. Maybe I'll go over to this. I'll go into chapter 3 and look into problems of chapter 3. And You'll notice that here you go. They did. Here's conceptual problems. Some of the conceptual problems. 3. Show these on a possible. This would be a good problem to ask, right there. You just have to draw something so it's fast. But if you didn't know it, you would have a hard time with it. Yeah. Also here shows the 3 physicals. Show the possible process in a PV diagram. Well, what the hell are they talking about here? That doesn't make any sense. I wonder what that means. Who cares? Boundary work. So that's probably has one that could be polytropic. Here's one with a linear spring. Just kind of did that. Any more? Here we go. I'll do Control F up in here. I don't know why it takes a while to get that back up in there. There you go. Poly. Nitrogen goes through a polytropic process with N equals 1.3. It starts out at 600 degrees Kelvin and ends up at 800 degrees Kelvin. Is the work positive, negative, or 0? Interesting. Is the work positive, negative, or 0? Then I go helium gas goes from 1 kilopascals to this right here to this in a polytropic process. How much work does it give out? That's a good question too. And then you go air goes through a polytropic process from 125 kilopascals to here. Find the polytropic element and the specific work. So it doesn't tell you how much right here. So and then a balloon behaves so that the pressure is like this right here, and where C is this constant right here. The balloon is blown up with air from a starting volume of 1 cubic meter to a volume of this. Find the final mass, assuming it is at this right here. All right, these are all good, like good tests right here. So let's try to do this one right here. I like that one. Is that one of our example problems that were suggested? 350. It is. So here's one that we would. Dr. Yevastrik thinks that would be a good one to be prepared to solve. So let's see. I think Layla knocked the camera, so we can just be all resentful at her. Let's all resent her. So I have 355, and let's write polytropic, and it goes from 125 here, so it goes P1 equals 125 kilopascals, and this is air, and T1 is 325 degrees Kelvin, and its final P2 is going to be 300 kilopascals, and T2 500 Kelvin. So find the so we want to find the polytropic exponent and then the specific work in the process. And by the way, I think we might be able to also here, maybe, we might be able to find the heat with it, because I don't think at this stage right here we were doing stuff with our U's. I think it might be true. I think so. But anyway, we know that a polytropic process, we have PV N is equal to a constant. And then we know that also we would have that the PVN is constant. So since they're constants, we can go like P1 V1N is equal to P2 V2N. So we can go either way with this. Go P. Well, a lot of times I want to go 2. Usually want to find out what 2 is, but it doesn't really matter because we have it already. And that's going to be V2 over V1 raised to the n. And then we know we could take the natural log of both of them. And then that's going to be n times the natural log of V2 over V1. So what is this? These are all absolute values, so that's a good thing to check. So we have, I said 2 over 1. 2, yeah, that goes 2 over 1. I'm going to double check that. I think I screwed it up. I did. My bad. Could have just stuck around with the other one right there, right? So 2's on the, let's see, 2's on the top, so 2 should be on the bottom right there. Yes, okay. Whee, brain, no working. So let's see, 2 on the top, so that's 300 over 125 equals n natural log of, wait a minute. Oh, I know what I should have done. Ideal gas law, or yeah, I think ideal gas law has to be used, right? Because we can't get the specific volumes from the tables. Let's double check this right here. All right, so first we'll get the right there, right? Critical constants. We want this. All right, so air is R 0.287, and then so ideal gas law is PV equals RT. So V1 is equal to RT1 over P1, which is going to be 0.287 and 325 divided by 125. So 0.287, 325 times 125 divided. And so 0.7462 cubic meters per kilogram. And then the same thing over here for V2 is equal to RT2 over P2, which is 0.287 500 over 300. So 0.4783 cubic meters per kilogram. I don't know why there's a parentheses right there. So V1 is 0.7462 over 0.4783. Therefore, N. Let's see, I could divide these, take the natural log of them, and then take 300 and 125. And take the natural log of that. I need to swap those around. Boom. And I get 1.9687, 1.969. That was the answer right there. And now they want work, though. And so remember that work is going to be equal to the integral of P dV. And therefore, little w is going to be the integral of P dV, like that right there. and that's going to be coming from 1 to 2. But let me think about this. It's going to be equal to a constant. We could find out what that constant is. I don't think I've done a problem that was identical to this, so I think I want to. I don't like peaking. Here's what I would do. We know a pressure, and we know two pressures and volumes, right? And we know this now, so we could actually find out what that constant is, and then we could write pressure is equal to Vn over that constant. And then we could put that back in here. I think that's how I would do the thing. I don't think we've done a problem like that before, have we? Anybody recall? Anybody give a shit? I'm sorry, that was not nice. So let's go ahead, and we got to be careful with our. I don't think it matters. I think we could just go ahead and put it in there. So we go 125 times 0.7462 raised to the 1.969 is equal to the constant. Therefore, the constant equals, so 0.7462. I'm going to swap those around, and I'm going to raise it to that and multiply by 125. Boom. And I could test this out to make sure that this constant works out. So I got the right math right here. We could also go 300 times 0.4783 raised to the 1.969, and that's going to be equaling to, let's see, I gotta draw my little line right here so I separate this thing out. This is the kind of way that I draw it when I'm just thinking the thing through instead of trying to make it look pretty on a engineering paper. And I would say when you're practicing doing problems, just don't use the engineering paper. I don't know if anybody would do that though, right? Because it costs money. But this paper costs money too. The engineering paper is not that expensive, really. I guess it is. Just talking to myself now. Oh yeah, so I get the same things. 70.22, right? So just some round off error right there. So anyway, here's what I would attempt to do. I would go V raised to the 1.969 divided by 70.24 dV. And this is 1 to 2 right there, right? So let's see, what do we generally do? We usually raise it up 1, right? So if we have, I know this is totally stupid on my part, right? So don't make fun of me. We usually go 1/3, right? X cubed, right? So we're going to add 1 to this and then divide it by that thing, right? So this would be V to the 2.969, 2.969, 70.24, right? And this would be going between V1 and V2. So we'll go, I think I'll just keep them over here to the side. 2.969, 70.24, and we're going to have V2, which is 0.4783 raised to the 2.969 and minus 0.7462 raised to the 2.969. So 0.4783, 2.969, raise it to that, and then 0.7462 62. It's gonna. I feel like this is gonna be too small of a number. 2.969. Raise it to that. Subtract it out. Comes out to a negative number, and we're gonna divide it by both of these. That doesn't feel right. And we'll do it anyway. 2.969 divided 70.24 divided. Oh, I made a math error. Son of a bitch. My bad. This is not true. This would be, P would be equal to the constant. I'm sorry, Vn. So that was just this is where, you make a simple little math error somewhere in the beginning and you cause yourself all kinds of problems. Shucks. So that's going to be a whole separate thing. So what would this be? This would be actually minus right there, right? That would be minus. Yeah, but this thing would have to be on the top. Yeah, sorry about that. And I bet there's a equation on our cheat sheet that has this in here already. Don't you think? I bet there is. I double bet you. Want to bet you? Someone has already done this math for us. I like to try to do it myself. I don't like to rely on things like that. So let's see. I put that in there. That's wrong. This is correct. So I'm going to go squeeze it in there, 70.22. And then, so now we're going to add 1 to this and then divide by it. So it's 70.22. And so that's going to be 0.969. But what do we need? Does it need to be negative? I think it needs to be negative because that's negative. I think so. I don't remember I should, but I don't. Negative 0.969. And now we're going to go between our two things, right? We're going to go between 1 and 2, or 0.7462 up to 0.4783. And 70 points here, negative 0.969, and go 0.4783 raised to the negative 0.969, and then minus 0.7462 raised to the negative 0.969. I can hear just people just like snoring in the background. All right. 0.4783, 0.969 negative raised to the thing. Okay, so that's 2 point. You can't see that, so that's the reflection right there. 2.4. Now you're 0.7462 raised to the 0.969, and then boom, and then subtract. Actually, it's not negative in the end, but that's okay. It's going to be subtract. So multiply by 0.70.22 and multiply 0.969. We divide, and so we should get a negative 51.85. Units are an important thing here. Okay, these are kilopascals, so that, yeah, okay, so it'll work out to, we're going to consider that to be a kilojoule for this thing. So let's see, how did we do compared to what they said that we were supposed to do. Or did I? There you go. We got it. 51.8. So that's what we did the right thing. We did all this convoluted junk and we came up to, it's very satisfying, right? Yeah. I know you don't care, but it is true. Now, if we want to go to the cheat sheet, so let's go to the cheat sheet and see what the find people of the FE book, the Lindeberg book. He's a good dude. Really helped us out by making that nice big yellow book. I should bring the big yellow book in. You don't really care what the big yellow book looks like, right? That wouldn't really matter to you. But let's see, if we wanted to use the real one, the polytropic for a closed system, here is one way to do it right here. Oh, we actually did cover this at one point right there, right? So we didn't have to do that integral. We could have, even though that looks like a capital W, it's actually a lowercase w because all of these things are on a per mass basis. We could have done, because we did write it down at one point, that the work was going to be P1 V1 minus P2 V2 divided by, I go 1 minus n, or is it n minus 1? Well, it depends on which order you put the thing in, but that would be the one. When I see people do this one right here, I'm like, that's just too much of a shortcut, I think. But you could have done this short. That shortcut is definitely true because we did have the temperatures at the beginning and the end. But I think you should find out what the specific. I think I should not have given you this. You could do the math and figure this thing out, but I don't like it. I really wish I had not given you this sheet because while this is true, it's really just a cop-out type of thing. So I'm going to have to remember that when I'm writing out the problems and make problems that can't be solved using the cheat sheet. But anyway, if you use this one, which is the proper way to do it, it was in the book. The other one was not in the book. So we go 125 times 0.7462 minus 300 times where'd you go? 4783 divided by 1 minus 1.969. Or the problem I would ask you is just to find the work, and I wouldn't ask you to find this, and therefore you would need to know that you had to find that. That would be the type of Dr. Deal problem, because then it could be done really quick, but you'd actually have to know something. 300.4783 times, and you subtract them. Ooh, that's interesting. I didn't think I would get a negative value. Didn't think I'd get a negative value, but it did. And then just divide by negative 969. Yeah, so I get point, but see, I get a positive value for right here, but it should be a negative value. Should be a negative value. This one gives us a positive value. Let me double check what that equation looks like. 1 and 1. I did 1 and 1. And n. Oh, there it goes. N minus 1. That's what I did wrong. This should have been n minus 1, and it would have given us the right. Yeah, I'll cheat. Negative 51.82 kilojoules. And then if you wanted to try it out the other way, this interesting thing. Okay, so if you did want to go the cheat sheet route, which I don't want you to, but you could, you can go W equals R T1 minus T2 divided by, you still need N though, right? So you go 0.287 and 325 minus 500 and divided by n minus 1, which is 1.969 minus 1, and you should get the same thing. I wrote it right there. So 325, 500 minus, and then 0.289. Did I write the 287? 287, I think. Times, and then 0.969 divided. Yes, you get the same thing. Okay. All right, so we have 2 hours under our belts worth of thermodynamics review things. I hope none of this junk right here was too overwhelming as part of it. I know that nobody wants to have to use their calculus. They just want to take the class and then never have to ever use it again. Or as many engineers like to do, especially engineers who are parents. Parents love to tell their children, and parents who are engineers love to tell their children, I never used calculus on anything. And I'm like, yeah, all right, you're just not that kind of engineer. Okay, that's cool. But anyway, it's necessary to revamp those skills on every level. So that's where things come from. So, but anyway, the important things on this is this equation right in there. We want to be able to use that equation in conjunction with the first law equations. We didn't have to really use it right here for this one, unless someone had asked us about the heat of this. So if someone had asked us about the heat, we might need to, what we would use in a closed system would be the U2 minus the U1 is equal to the Q1 to 2 minus the work 1 to 2. All right, so we just found the work for this right here. The U2 to U1, because it's air, we could look this up, right? We might need the mass to do this because this is on a per mass basis. So we might go like this: U2 minus U1 is equal to Q1 to 2 minus work 1 to 2. And now this is what we found right here. And we could look up this U2 and this U1. And this is definitely something I would ask you to do, something along those lines, where you would either find this from here, not here, right here, right? So we could find what the U was going to be. We started out at 325, so we need to interpolate. So I probably won't ask you to interpolate except maybe once in something. I wouldn't make you do it multiple times. Oh, this is all, I got to remember this big hint that I'm going to tell you after here in a second. But we would use this guy right here. So we go between these two right here. See, I would ask for 320 instead of ask for 325 as part of that. And you could get what this is between here, and then you would be able to get what this is right there because you got this, right? Because you got this right in here. And I would expect you to use this equation right here for a polytropic process and not waste your time doing this right here, because this did take me some time. But I might ask a question along the lines. So this would be an even more of a problem that I would do. I might ask you to find me the heat in this process. And then what you would do is you would find the work and you would find the internal energy, and then you would find the heat. Alternatively, instead of looking these up, I might have you say to use a constant specific heat. Because one of the topics that we did cover during this session was specific heat. So we might use CV of air for that instead of looking them up in this table right here, right? I was just about to say something that was going to be a major hint for the thing. I can't remember what it was. That's kind of mean of me to say, isn't it? Oh yeah. Okay. So yeah, major hint. Sometimes I might ask, because I don't want you to interpolate, And if I were to use something besides steam, because steam, like something in the B tables, so like if it happened to be like refrigerant or ammonia, which is a refrigerant actually, or carbon dioxide or something like that, they don't have the indexed ones by temperature. So what if I had to, in a problem where you had to look up the temperature knowing the pressure, I probably would like get as close as I possibly could to so that the results would match up with the pressure, and so you'd be able to find the temperature. Does that make sense? So I'm telling in terms of a hint of what I would do, because I want to make the exams shorter in time. I would find a way so that you didn't have to interpolate. So like if the number comes out to, let's just pick this one for instance, in the carbon dioxide, if we went through some condensing process and for whatever reason we had to do, and we ended up with a pressure, we needed to know a temperature. And I don't think that's an actual scenario, but something similar to that I have run across. I would make the numbers work out. So you end up getting 1,525, let's say. Well, then just go ahead and use 28 degrees. And don't bother in trying to interpolate between whatever that would land. So I don't know. I don't know if that's a hint or just letting you know I'm going to try to minimize the amount of interpolation, because that's a time-consuming thing. And once you've demonstrated you can do it, I don't need you to keep demonstrating it. Which in other, which I'm saying mostly because if you take a look at the Dr. Yevistruk's exam, and I highly suggest that you do, because I'm teaching this course for the first time, and therefore I would definitely try my best to keep it consistent with the other professors that have taught the class before in the things that they're measuring. But if you could see in this problem right here, for instance, I had to interpolate a whole bunch of times. If I were to ask this problem or a problem that nearly identical to it, what I would end up doing is trying my very best so you didn't have to interpolate at all, right? So the things that I would ask for would work their way out so that there was no interpolation needed. Or if there was an interpolation needed, it would only have to be done one time. So that's just a hint in when looking at the exam, while working on the exams. Like if you feel like you've had to interpolate a whole lot, I didn't do what my intended thing was. All right, so I'm tired of hearing my own voice, and 2 hours have gone by, and I think that's fair amount of things to have covered. I think we covered some pretty good problems, I think. I'm gonna try to go back and see. We did 440, 449, 479. We did 111. We did 355. Yeah. So in 2 hours, 1, 2, 3, 4, 5 problems. Although I think problem 111 was wicked too long. I think we probably spent 45 minutes on that. Let's see. Alex has a suggestion. Where did he go? Oh no, that was just directly to me. Give the students who took the time to come. Thanks, Alex. I'll consider it. But I'll most of the time I consider that type of thing. But what I will do, let's take a roll call here. Although I didn't. No, actually, that oh yeah, it gets saved. The roll call gets saved when we do it in Collaborate, and I know how long people stayed. It keeps a log. So I'm going to be done. I'm going to cancel out, and I'll stop recording now. I really appreciate